shall we? Yay, so we are live. Alright. So, I'm gonna do a window capture of, I guess, window will be, yes, where is Microsoft Edge? Yes, this. Okay, cool. Okay, you all, can you see my cursor moving? Okay. Cool. So, we're gonna do electrostatics. Right. Actually, we're gonna do electrostatics. Let me tell you the syllabus for today, which is, by the way, no one's gonna come on the live chat so I can be free. And oh, that's a nice. Okay. Alright. By the way, ignore my face. I have some stuff going on. So, syllabus for today is that we're gonna write all the formulas for electric charges, basically electrostatics, potential stuff, and capacitance. Wait, let me write that down, okay? Electrostat. Okay? And we're gonna do potential is in this one, okay? So capacitors, and we're gonna do current, and electricity, and we're gonna do moving charges and magnetism, and matter, and we're gonna do EMI, EMW, and of course AC. This we'll do AC before EMW of course, okay? So this is the plan. Let's get started. So all we have to do is just revise and basically write the formulas. So okay, oh, and by the way, let me tell you that all these slides and study material belongs to this guy. Yes, Pradija, an excellent teacher, absolutely he's brilliant. Yeah, so I'm not stealing his work, it's just I'm studying from he is my teacher. I have bought the subscription of Unacademy. I'm not here to advertise for Unacademy though, but yeah, for him. Because, okay, wait, let me do one thing real quick. So, a little less will be nice. Okay, we're good. So yeah, let's get started. I'm gonna keep a small yes, that I need. Right. Now we'll study non-stop top speed till 6 a.m. in the morning or 7. I just try not to fall asleep, so I'll be writing stuff down in my formula sheet, I'm making a formula sheet. A pen. Right, yeah. So this is for electrostats. Right, yeah. So this is useless nonsense. I'm gonna skip. Wait. I'm gonna skip. Oh. Come on, what's the deal with you, bro? What's the deal? Why'd you be hitting like that, man? Okay. Yeah, this one that's useless. Pointless, okay. We gotta write the charge on electron, we know. Quantization of charge, yeah, we know. Conservation of charge, yeah, we know. Right? Okay, identify incorrect for electric charge Q. What the hell? Contain something such as such. What? So I'm facing errors, but who cares, right? Let's get back to work. Okay. Yeah, we all know the answer for this. It's transferable, so that's wrong. We have done all these MCQs before, but yeah, we need to practice again. Body can be negatively charged. Stupid, just stupid. Okay, Coulomb's law. Okay, let's write down the first formula. Coulomb's law, right? You can write it down too. Well. F12 equals F2. Okay, that would be, yes, F equals KQ1 Q2 by R squared, and we know K equals 1 by 4 pi epsilon naught, and we also know that it's K equals 9 into 10 power 9 Newton meter squared per Coulomb squared. Write the units too, like what's the harm? And it will definitely come in from like dimensions, units and measurements chapter. So, okay, permittivity, that's also really important. R equals E by E naught. Okay, cool. If you're suffering any buffering, I don't really care. I'm just kidding. Actually, I don't, because no one's even here, so. Okay. Yeah. So net electrostatic force in a medium. Ooh. Well, we already know all this. So yeah, if it's in a medium, the force is going to be F naught epsilon R. That is what constant? The dielectric constant, yes. Okay, we got it. We got it. Let's do hurry, okay? Yeah, this easy questions, What is this? Two identical charge spheres are suspended by strings of equal lengths. The strings make an angle of 37 degrees with each other. When suspended in a liquid of density blah blah blah. Oh, the density part. We know that density equals mass by volume. And wait, what's the relation between the delta constant of the liquid is he made a cross on this, so I don't think we need to do this. Okay. I can't really wear my glasses because it hurts right here, but I can't really see without my glasses. I'm nearsighted though, but still. Gotta work with what we have. Gotta do what we gotta do. Alright, so if distance d, okay, so two charged spheres separated by distance d exert force on each other, blah 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 blah. The dielectric constant is 2, so the whole force will be divided by 2. Easy peasy lemon squeezy. Alright. Bullshit. Easy questions. The Coulomb force is dominating force in the universe. No, it's not. Which is the dominating force in the world? Can you tell me? I guess it's the wait. It's not the it's the gravitational force, right? Yes, it is. And suppose the charge of a proton and an electron differ slightly. Yeah, this is a very nice question. I remember doing it, so like it was kind of hard too. So we don't need to find the exact value, we just have to find the order. Okay, so I'm going to solve it right here. Okay? I'm going to solve it for you guys. So we're like giving God. Suppose you're not able to see the questions, I guess. Let me zoom out a little. Are you now? Yeah, I guess most of it is visible now. So suppose the charge of a proton and an electron differ slightly. Okay. Right. One of them is minus E, and the other of them is E plus del E. Okay. So we're talking about a proton and an electron. So this will be positive, and this will be definitely negative. So this is Q1, this is Q2. Is the net of electrostatic force and the gravitational force between the two hydrogen atoms placed at the distance d much greater than the atomic size. Okay, so the d is like much greater than the atomic size. Apart is 0. What? That means the net of them is 0. That means this equals this. Okay. Woo! So since this is very small, so I'll do. Yeah. So we know that Q1, Q2 R squared, Q1, Q2, R squared equals, what is the formula for the gravitational force? Well, it's G, M1, M2 by letting in R squared. So we can like cancel this out. Yeah, we can cancel this out. Yucks. Okay. And then we know that mass of electron is negligible, so we gotta write this. I'm not considering the signs because it's not really necessary. Still, you don't forget it. This plus del E, okay, equals G of proton, okay? Do you know the mass of proton though? Yes, it's given. Okay, so it's charge an electron 0.6 into 10 power minus 19 times 9 into 10 power 9 into this 1.6 into 10 power minus 19 plus del E is what we have to find, equals, we know G, the value of G is 6.64 into 10 power 11, right? Minus 11, right? It's minus 11, right? It was minus 11. Gosh. Yes, I was right. It's 6167 now, but it doesn't really matter. I'm good at that. Okay. So we're gonna cancel all these. Okay. So this will go there. Okay. So the new thing will. Oh, so we already knew the answer. Now we know the answer, but we're still gonna do the calculation. Okay. So it's gonna be 167 into 10 power minus 11. Fine. 1.6 into 10 power minus 19 into 9 into 10 power 9, and yes, and this will be 1.6 into 10 power minus 19 plus del E equals this. So this, I'm gonna take this away, okay? It's gonna be minus 1.6 into 10 power minus 19. So after doing all the calculation very carefully, we figure that this and this become, what is 19 minus 11? 8, 0. It's going to be 8. And this makes it minus 1. And this makes it 6.67 into 10 power minus 1 upon, well, 1.6 into 9. I'm gonna say, I'm gonna cancel 64. 1 and 4. Somewhere like it's gonna be 4.1 and 2. 4.1, and I'm gonna, let's do it 4.2 so that we can divide it by 2 or 3. Okay, so it's 3 9s are 3 3s are, and it's 3 1, 3 times 1, and it's 12 4. We have 1.4 10 power minus 1. There is something wrong. Oh, so the mass part. Oh God, we forgot to multiply the mass. Oh man, dang it. Yeah, so we also got to like 1.4 into 10 power minus 1. We also got to multiply this part. That is 1.67 into 10 power minus 27. Yes, remember this one, okay? Minus 1.6, it doesn't really count. Okay, so this becomes 1. Do we really gotta do it? 1.4 and 1.6. That makes it, God, 24. 6, 1, 7, 8. That's 4, 12, 2. It's 2.24 times 10 power minus 27. 26. I mean 28. And minus this. Are you sure? Are you sure we're gonna subtract them? I did it correctly earlier. I don't know what happened. Shit. I'm stuck. Where did I go wrong? Man, something is wrong. Where did I go wrong? I messed up. I don't know how though. Can you spot where I went wrong? Basically where I fucked up. Oh man, now we gotta do it again. Oh gosh. Everything was so perfect. I did it earlier, I remember I solved it with much ease. I don't know what went wrong, and we don't have time to waste on this problem. God, I'm gonna do it alone later. Gosh, I'm not gonna waste my time on this. I'm not gonna waste my time on this anymore. I'll do it later for sure. And if you got it right, then that's great. If you got it wrong, then you're stuck too. I gotta do something like okay. Charge Q is placed at the center. Of the line joined to exactly equal positive charges. Q, the system of the three charge particles. Charges will be in equilibrium if Q is equal to. Well, center of the line and two exactly equal positive charges. Oh, we know this shit. There ain't not much in this. All we gotta do is equal this force, equate this force to this force, and the force exert each other, and then this kind of shit. Oh, man, we gotta hurry. It's already 2. Okay, we know. Let's make the formula sheet. Let's fill it. Okay. So that's F. Well, F12 equals F21, right? Gosh. Yeah, whatever. Move on. Yeah, this question was pretty cool, pretty cool. So what are, if you imagine, okay, yes, finally we're at the electric field. So, electric field. So let's write the stuff down, y'all. So it's basically field equals force by charge. That is our test charge. Right. Force and charge Q due to E. Okay, so there's electric field, and it will exert a force on any charge on the test charge. So we won't count the charge of the test charge because it doesn't really matter. So the force will be exerted by some electric field, and that will be the Q times the electric field. Right? Right. Okay. So the force vector will be electric field, Q times electric field. Q will be the charge. Okay, right now we're exerting a charge, force on charge Q, which is not a test charge. Okay, if it was a test charge, then we'll just get electric field, not a force exactly. Because yeah. So if it's an actual charge, excuse me. Okay, so yeah, let's. Yeah, we know the direction part. The positive is like it attract, it like repels the electric field, like diverges, and the negative charge converges. So everything is like coming. Negative one is like a black hole, and the positive charge is like white hole. Yay! If you are negative, you're a black hole. You're sucking everything. Sucking electric field in. What is a test charge? We know. Crap. I call easy stuff crap. Okay, it's not actually crap. Okay, so force equals KQ times the test charge. So electric field into the distance, right? Okay. Electric field is basically the force. It's basically the force. It's just we have a test charge, then you gotta divide it by that. The force, yes. Oh, come on. And yeah, field lines are not real. Yes, we all know that. Get to the point. Yes. This is a nice question. So we know that force equals Q times E. So if an electron is exerting a force, then it will be its charge times its electric field. And if we want to find the acceleration it causes, we know force equals mass by acceleration. So we gotta divide it by its mass, and we get acceleration. Yeah, so that's things make so much sense now. Acceleration equals E times the acceleration of that's the acceleration of the electron. No, actually, there's an external electric field. Right, from any charge, and then that field is exerting a force on the electron, okay? And that force is equal to the force electron exerting back. Right? So yeah, whatever we say is not wrong. Anyways. Sorry. Yes, this is the parabola path. Yeah, if there's no gravity, yeah, you know that, right? You know the equations of parabola? Yeah, we gotta find out the equations of parabola. They might ask us to find, we just gotta replace the mechanical variables with the electrostatic ones. Right, like, I gotta drink some water. It's been 30 minutes, guys. It's literally been 30 minutes. It's kind of really creepy to watch myself in the past. Like, the stream is lagging, right? A little. So I can see myself doing the same stuff I was doing like 5 to 6 seconds ago. That is creepy. Cheers, y'all. We'll start. My back hurts. I've been sitting like this for like 14 hours straight. This is free time. You can play some music in your head, not out loud. Because we're putting a ban on music because it is making us its slave, kind of. Yeah, you know, like I was like in that state where I could like not spend a day without listening to music. Come on, and not one song, 2 songs, 3 songs, like a full on playlist. Like that was crazy. Okay, this water break was quite long. I took so long to drink water. That's insane. Alright, let's get back to work. Okay, man, that's insane. Chloe did take like 3 minutes. Okay. Should charge us here in 3 QRs. Come on. We know the separation part. What's this? Why is it here? I guess there's some catch in this. Do you want to solve it? Should we solve this? There's a thing, a plus minus, a joker here. I don't think I'm gonna... I guess I will be able to solve it. This actually looks like a tricky question. Look at the options. They'll kind of like look very, like mastermindedly plotted. I think I'm gonna go skip it. 4 charges are arranged. Yeah, we know. Okay, electric field due to infinite charge. Oh yes, this is very, very important. Okay. God. Mosquitoes. So many mosquitoes. Sick of it. Sick of the mosquitoes, for real. All out. It's like there, very far away, and I'm not moving from here for you guys. Although none of you guys are here. Alright, so let's get to the work. Oof. Yes, here's the slide. Okay, so now we're finally entering the amazing work. Okay, so this is EF due to infinite charge rod. Okay, so E perpendicular will be 2k lambda by d, and parallel would be 0. And we know that lambda equals charge by length is the linear charge density. That's why. So lambda also equals dq by dl. Right. And we're not going to get into the integration part because we're just not going to get into it. It's not like necessary, right? So E parallel is 0. I'm going to write that down here too so that it's like visible. Okay, these are the formulas. Write it down, y'all. In the case of infinite long wire, electric field is proportional to 2k lambda by d. That's d is r. That's 1 by r. Yes. All right. Electrostatics plus circular motion. Yes. Time period. Okay, yes. Let's do it. That's like really importante. I'm gonna use a green marker to. I think I should use red. Red is a really powerful color. Or should I use orange? It's a contrast. Found red. I'm gonna use red to underline the infinite rod and electric field. Right? Yes. Cool. So now we're going to do the electrostatic plus circular motion. Just remember that T equals 2 pi r root m by 2k lambda q. Man, this formula is scary. We know angular acceleration equals omega square r. Right, yeah, but okay, this is the derivation he did. So we know that F equals QE and F also equals Q. Okay, that's the electric field. Okay, yeah. F equals charge times the electric field due to the rod. And we know mass into acceleration equals F net. Okay, yes. And angular mass mass into angular acceleration equals the same thing, which is going on in here. And we know m omega square r, which is the same thing, equals 2q k lambda by r. So we get omega from here. So I think I'm going to write this down, this whole thing. MAC equals Q times electric field, right? And M omega square r equals Q 2k lambda by r. Yes. And omega equals 2kq lambda by m r squared whole under root. This is where we get the omega. And then we have time period equals 2 pi by omega. Let's put the values. And we get the answer. Yes. That was a really cool question, I'm not gonna lie. Oh yeah. EF due to semi-infinite uniformly charged rod, okay? UCR, that's uniformly charged rod. Okay, we have a semi-infinite rod here, and we have the electric field here. Big box here too. Cool. So let's write the formulas that E perpendicular equals K lambda D. That's basically the half of the full one. And E parallel is also K lambda by D. So E net equals 2K lambda by D. Okay, that's basically the same as thing. We divided the infinite rod into like two parts, right? Alright. Now, due to a ring, uniformly charged ring. Now, EF due to uniformly charged ring. So, that makes it, oh yeah, I love this formula. E equals K Q X upon A squared plus X squared whole raised to power 3 by 2. This formula is like good. X is R. You can name X as R, but it's not the radius, right? So X is basically the distance from the stuff, and A is the radius. A is the radius, okay? Is that clear? I hope it is. I kind of miss Andromedy out of nowhere. I watched Mahabharata. Oh, come on. What am I talking about? Alright, let's not get distracted. And okay. This is the graph. The maximas are at a by root 2 and a by plus minus a by root 2. Okay. E max equals plus minus a by root 2. I forgot why it's that. We did the derivation for this too, I remember in the long course classes. But I kind of forgot, like, why. Okay. Electric field due to infinite sheet. First, let me circle them. Okay. Electric field due to an infinite sheet. I should have drawn the diagrams too, but I've done it like plenty of times. QA, we know the surface charge density is sigma. And so we know electric field equals sigma by 2 epsilon naught. This is very important, you know. This will come really handy in that chapter, capacitor. This will come really handy in that. And it's like also constant. Right? And it doesn't really give a shit where is, I mean, what's the difference, I mean, distance from the sheet, right? Because it's an infinite sheet. Ooh, I like this question a lot. A lot. So EF is along the axis of symmetry. Okay. Basically, the formula for this is, yes. Let me do it. Alright. Due to an infinite sheet. Okay, this is for infinity. This is also for infinity. This is for a circular ring. This is for semi-infinity. And this is for, forget it. Okay, so like now we are due to a circular arc. EF due to a circular arc. Guess what it is? E equals 2k lambda, familiar, by r. Okay, that's for the infinite rod, right? That's for the infinite rod. And sine theta by 2. Okay, but we kind of like know that. For like an infinite rod, it's like 2k lambda by d2. And for this one, it's the same too. It's just an extra sine theta by 2. We don't need to consider the signs because we'll like do the find the directions manually. We can do that, right? Of course we can. We're not afraid of anything and anyone. And if you put like theta 180 by 2, that's 90. Sine 90 is 1, so that's basically the EF due to a circular, semicircular arc. So we don't need to like write it from like, write it for like a second time. It's the same thing. It's just the arc is semicircular. So yeah, no shit. Okay, we're halfway there. You're halfway. A charged wire is bent in form of a semicircular arc. Is the wire finite though? Is the wire finite? Wait. What about the finite wire? We don't know how to. What about the finite wire? Yes. What about the finite rod? We don't know anything about it. I kind of remember integrating due to a finite rod. Do you want to solve this one? Okay, A charged wire is bent in the form of a semicircular arc of radius r. If the charge per unit length is lambda, the electric field at the center O will be. God, come on. We just solved it. It's k lambda. It's k 2k lambda by d sine it's 2k lambda by r, same as that for the infinite rod, remember? Yeah, so that will be this, because let me show you. Where did the pen go? Where did the... Come on. Don't shit with me. Where did it go? Oops. My sketches fell out. Do you want to see? Yes, I made it. Kind of random though. I also made this cute little bird. Ooh, she changes skin color. Alright. Enough nonsense. Let's get back to work. Not able to find my pen. So what am I going to do? Seriously, where did it go? Well, I have to check the recording. Where did I put it? It used to be here. Really? Really do. It's vanished in thin air. God. I put it in my bag. Alright, so let me show you how it's done. Okay. So basically, this is 2k, what was that again? Yeah, lambda by, what was that again? R, that's A, right? Okay. So it's 2, this is 1 by 4 pi epsilon naught, so I'm going to write it as 4 pi epsilon naught lambda times A, okay, fine. This gets cancelled and it becomes lambda by 2 pi epsilon naught times A. See, we're right. That's how it's done. Okay, electric field at the center of a uniformly charged semicircle of radius A. Well, we just did that. Oh, potential energy. Very important topic. Do not skip it. So, wait. Can you guys just, like, ignore my weird accents? I don't have one. I would really appreciate if you would, just because I'm studying. So finally we come to the potential energy part. I hope you guys kind of, you guys have remembered all the formulas we've been through. Have you guys? I really expect you to, because we don't have time. Oh shit, it's 2:49. Come on guys, what the hell are we doing? You gotta hurry up. Okay, wait. I'll be right back. Okay, I'll be right back. Or maybe not. Do you guys need a break? I don't think we like need a break. Alright. Okay. Dang, it's been up in here for like 55 minutes and still no viewers. Oh, dang. Actually, it makes sense because I'm like shooting literally at 2:50 a.m. I'm awake when everyone's asleep. That already makes me one step, actually many steps ahead of like 90% of the people. Anyways, let's get back to where we were. Man, if you're listening with me, which you probably are not, right? Nobody's here. Then you're probably ahead of almost like a lot of people. Like, anyways, let's start. What? That. Okay, potential energy. Yes. Ooh, finally a new topic. I'm gonna mark potential energy with green. That would be nice because it will differentiate easily between electric field and potential energy. Right? Yeah. There's potential energy. Right. We got you. Okay, so first of all, we are going to write this down. Okay, first we're going to write that del U equals minus of negative the work done. Also, work done equals U initial minus U final, which is basically negative of the delta of the, which is negative of del potential energy. So we can write it as work done equals minus del U and vice versa. Cool. Who cares? Okay, what is potential energy? So we have U equals K Q1 Q2 by R. So we just have 1 R less. Basically force just divided by. So U equals force times R, right? Force times R. Force times the distance. And potential energy at infinite distance is taken as 0. So we gotta find, whenever we're talking about potential energy, we gotta define a point where potential energy is 0 for reference. Okay? So at infinity, we're gonna assume that potential energy at infinity is 0. So, if that's the case, then the potential energy between two charges separated by distance r is going to be kq1 k times the charge in 1, charge in 2 upon the distance between them. Yes. So, yeah, and also always consider, because this is a scalar quantity, always consider energy with the signs. What are these? The charges with their signs, right? Yeah. Cool. In bringing an electron towards another electron, the electrostatic potential energy of the system. Okay, electrostatic potential energy of the system. In bringing an electron towards another electron. Okay, so they already repel each other. So if you it's like a spring. Okay, there's a force, and if you will bring them together, what will happen? Of course, the potential energy will increase. You will experience a greater force. Okay, that's easy. Find potential energy for the system of the particles if all the particles have the same charge Q. Okay, so the formula for this one is a potential energy on 1 due to 2 plus on 2 on 1 due to 3 plus on 1 due to On 2 due to 3, yes. That's the sound that this pillow is making because I'm sliding it down. So friction and stuff. And, okay, I did not, do that. Okay, the formula is you know what? Let's write it down. The formula is this. I remember Pratik Jan started telling a trick. Something important here. I'm not getting it. Okay. So, of the system is basically potential energies of all the particles, right? So we gotta add the potential energy of all the particles between these two, and these two. Yes, basically the force between these two, and these two, and then divide them by their respective distances. So in this case, since they're all identical, we can so U of a system equals U 1 2 plus U 1 3 plus U 2 3 blah blah blah. Right. So this is the potential energy on 1 times the number of particles. Yeah. If the cases are identical. Right. Okay, I'm gonna take another real quick water break. Okay, we're half the way there. Still a lot of shit to unravel. Realize. Not unravel because we've already unraveled enough. Yes, so it's basically electrostatics. I mean the field part is complete. Now we're at the energy and potential. That's what we'll be doing. Yes, we did that, and we also did this. And okay, these are all identical too. We just gotta find the distance from here to here, and that, my friend, will be. You gotta find this diagonal of a cube though. Yes, you gotta know that. I'm definitely going to forget the formula for the body diagonal of a cube or cuboid. So let's just write it down. Cube diagonal equals root 3 by 8. Yeah. And for cuboid, which they might ask, there's a high probability. Okay. Oh no, I know the diagonal formula for cuboid. I remember. It's the root of all that. It's sides. It's length, breadth, and height. Okay, the physics-aholic points, if the distance between two charged particles remains the same, then the change in their potential energy is 0. That, my friend, is a really important physics-aholic point. That if we will forget this, well, we're done. We're really done. First of all, I'm gonna do my thing. And yes. And yes, baby. Okay, so I'm gonna write the physics-aholic points right here. Really, 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 really important. So, if R remains same, del U is change in potential energy is 0. of course. Example, electron revolving around the nucleus. So in circular motion, there is no change in potential energy, so the energy is constant. Yes. Yes, it's not like there's no potential energy, but it's like constant. It's not changing. Same goes for here. Yeah, so this will come in handy when we're talking about stuff like work done, finding out work done and stuff. Because work done equals negative of the del. So negative of the del potential energy. This question is way so freaking easy. Like, it's kind of scary how easy the question was, because it looked kind of hard. You want me to solve it, guys? Just really easy. So there's this charge Q. Of course, the distance remains the same from this point B. So there's going to be no change in potential here, no work done here, but the work done will be done from here because the distance changed from A and B are at the distance of 2L, so that's basically L. It changed from L to L, 3L. And that's easy. Just put the value 2L first for the distance, and then roll that again 3L and subtract them, and of course it will come in positive because we're subtracting smaller from greater, and we already got to negative this, so if we will no. Wait, what? No! Oh, we gotta subtract the initial, yeah. No, it shouldn't come in negative though. I don't think it should come in negative, because like it should come in positive, because we're gonna subtract the final minus initial, and then we're gonna it will come in negative. That's true. Two charges Q1 and Q2 are placed 30 centimeters apart. A third charge Q3 is moved along the circle of radius 40 centimeters. I don't. Come on, distance, like. So the distance here was this, and then it came down, and the distance is like 10 centimeters now. You can clearly see that. The work done. A third charge Q3 moved along the circle radius. What? The change in potential energy of the system is this. Find K. Oh, we just gotta find its initial potential energy and find out and subtract them both, and then just put the value in. So we see the distance is not really changing. Is it? No, it's not really changing for A, but it's changing for this one, Q. The distance is not really changing for A, if you will see. It's the same, it's literally the same. This is 40, okay? But it's changing for it's changing for Q2, right? So the initial distance from it was this, which is 50 centimeters, but then it changed to 40 root 2 centimeters. Well, I think something's fishy. I think we should solve this question. I really think that. Okay, it's almost 3. Oh, it's 3 a.m. Okay, let's solve it. It's a really good decision for me to wake up and stay study with you guys, because I would have been like sleeping, wasting my time. Okay, so we have a triangle here. This is 50, and this is 40, and this is 30, and this whole length, this is 40. Right here is Q3, and then right here is Q2. Oh, no, wait. So the first initially, it was experiencing a repulse in this direction and in this direction. So this will cancel out. It will be like, if we will vector this out, it will be like in this direction and in this direction. It will be like smaller. Okay. It will experience a force in this direction, and if we will vector it out, it will be in this direction. It will be in this direction. Okay. And from here, from this one, it will experience a force in this direction. Okay, it's not like doing anything because it's black. Let me show you, okay? So, due to this one is this, okay? And now we have like this component and this component, right? So this will add up. Okay. So this is what? Oh God. This is this is 90 degree, and this gotta be. So it's like this is longer part, this is shorter part. 4, 3, 5. So this will be 53, 53, and this will be 37. Right? Yeah. I think we're doing more work than we should be doing. I don't know. Let's write it down. K, Q1, Q2 by R. Ouch. Ouch. Minus K, Q1, Q2 by R. Final. This was initial. This was final. And if we will subtract them, the radiuses are, the initial radiuses are, wait, you gotta add them too. Man, this is a really nice question, I'm not gonna lie. This is a really nice question. So, plus, first we gotta add a plus, right? Yeah. So on 3 due to 1 and on 3 due to 2. So the distance from here will be K, Q1, Q and Q3, Q1 is 40 plus K, Q3, Q2 is 50. Right. George, makan. Whoa. I'm like so close to the camera. I should relax a bit. Man. Oh, I'm tired. Should we take a break? Alright, we're like halfway there. A 5-minute break, okay? 5-minute break. Okay. I'll be right back. Okay. Oof. like go eat something, that would be nice. Alright, so this is gonna be a little stupid mukbang, but okay, I can make coffee too, because I'm too lazy. I will be eating drinks though, but again, too lazy to make that, okay? So, I know it's been 5 minutes, even more than 5 minutes, but come on, I gotta eat noodles. I made it way too spicy. Worth it. I can at least get me some water. You guys can go eat something too. Or you can just watch me eat. These are not that great, but since I made them, I can make any stupid, tasteless noodles taste delicious. If you're wondering what happened to my nose, I'll just don't ask. Just don't. चलो जब तक मैं खा रही हूँ रिवाइज करो. That's all the stuff I taught you, okay? With my hard work and love and passion and everything. The slides that I made myself. I'm really sorry. Please don't sue me, Pratik sir. Please just don't. These are your slides. Okay, come on. There's literally a. What is that? There's literally a watermark of Physicsaholic. That's his brand name. Kind of cool though. Don't be shy. Go on, eat. Wow, these are like really spicy. You know, too lazy to even pour it out in some other dish. finished. Alright, I'll be right back. Okay, stay right here. Alright guys, I'm back. I made myself some dalgona coffee. I'm not consuming it too much because I already have coffee more than I should have. Oh dude, just look at this though. Look at it. Isn't this just awesome? I did such an incredible job. Come on, just pay me like $200 already. Alright. This looks good. Cheers. आती है हमें राज बताते हैं कैसे हम बदलाए. Just like the YouTube play you guys a song. I'll play Nakamchura. Should I play it? Should I? No. Come on, let's get back. Move, okay. It's time to get back to work. I'll finally read the potential. Yeah, that. This is just so awesome. I should have put more coffee in it though. I can't believe I did such a great job. Back to potential. So now potential is nothing but just potential energy by charge, discharge. Yes, that's it. I don't think if there's anything that we would like. Oh yeah, the thing about potential difference, just that's important. Potential is defined as potential energy per unit charge, and the potential difference between 2 points don't depend on the reference point, but potential at the point depends on the reference point. Alright. Let's not play around, but what it actually is trying to say is that potential doesn't require, potential difference doesn't require any reference point, but potential at a point depends on the reference point, right? And also potential difference or potential scalar quantity like potential energy really focusing on coffee more than potential. Looks like coffee has more potential. So, that was a very bad, terrible joke. I have no humor. Seriously. If you find yourself laughing at my jokes, just come on. You have a terrible sense of humor too. Together we work out. Anyways, so force equals charge times electric field. We all know that, nothing new. So what is it trying to say here? So potential energy equals Q times potential. Okay, yeah, should we write this down though? Where's my pen? Oh, where am I in school? What's in this? And right here. Let's come on, I can't stay without it. I gotta play. Come on, just one, just once. I'm gonna play. You know what? Okay.
जब कोई अपनी बात अपनी बोली में नहीं कह पाएगा तो हुनर कैसे बाहर आएगा?
Really? Okay, so I gotta enjoy, okay? Let's get back to work, okay? Okay? I had so much fun with you guys tonight. Okay, that came out wrong, but seriously. And if I kind of had to if I was kind of slightly cringe, please excuse me. It's gonna, come on. Okay, stop. Steady. Alright, so we have okay, point charge. Electric field, for a point charge electric field equals KQR squared. V equals KQR KQ by R, and force equals KQ1 Q2 by R squared, and potential energy equals KQ1 Q2 by R. Right? And take Q's with their signs in cases of these two. The potential energy of charge Q kept in the potential V. Well, this is the potential. And the change in energy equals the change in potential times its charge. Easy peasy lemon squeezy. Right. I'm getting hiccups. Who is missing me? Is it my subscribers? I don't really think so. I'm starting to sound like Lois from Peter Family Guy. What was the show? What was the name of the show? I forgot. It has Lois, Peter, and Stewie, and Meg. Whatever. Okay, the potential due to the shown charge configuration at point O, assume all the charges to be identical. Ooh, we gotta find the potential, right? So, potential is basically nothing but it's electric field upon the distance, right? Yes, exactly. So, times distance. Yeah, I meant that. Okay. That would make it Yeah, that's pretty much clear. Where's my pen? Great, I lost my pen again. Okay, yeah, whatever. So the answer is V1 into 4. Or there are many ways to find the potential. Like we can do it like from the energy part, or we can do it from like the doesn't really matter. I think we should focus on potential and energy because we would know when it's 0 and when it's not, right? So like, yeah, whatever. Do you want me to solve it? Like in my way? I can do that. Ooh. What happened to my graphic tab? Oh, he's old. I gotta treat him with respect. Alright, so we have a charge for Q4, Q1, okay, they're all identical, they have the same distance, so that means the potential energy will be 4 times potential energy on 1. And that will be KQ by R, Q and Q2, and that would be K Q squared by R divided by R, that will be K Q squared by R, and since they're 4, that will be 4KQ squared by R. I mean no, R. And A is not R here, okay? We gotta check what A actually is, okay? So A is the distance from the, let's say this is exerting a force on this is exerting a force on this, and this is exerting a force on this, it's like this. And so these three forces are there, in which this one is exerting a force in this direction, which means this will add up in this direction and in this direction. So, the distance here, oh wait, they are all identical, but their distance isn't. So like the distance from like so A is the distance from this charge, but the distance from this charge is also A, and but from this it's not A, it's root 2 times A. So that's what he did, okay? He did like kind of it's V1. How? That's not... Oh, we gotta find the charge in the central. Gosh. I am really, really stupid. We gotta find the charge on this, so it will be... okay. We're gonna use this formula, 4KQ squared by R, and R is nothing but the diagonal, which is... diagonal of the square is what? Root 2A. And half of root 2a is what? Root 2a by 2 becomes a by root 2. Yeah, but wouldn't we prefer it this way? I guess. I don't think we would. Yeah, because root 2 will go up. So it will be 4 root 2KQ squared by A. And in the end, it will be, yes, we're correct. Correct answer, yes. Alright, next question. 4 electric charges, plus Q, minus Q, and minus Q, are placed at the corners of a square of side... Oh, this one looks... The electric field potential can I like stop? my throat like hurts, so I'm gonna stop speaking for a while, okay? If that's okay. Oh my god, guys, we're like almost 2 hours in. And from we, I mean me. Because there ain't none of y'all here. Did you hear that? Probably you wouldn't. Because that was a sound of dedication. Which you do not have. Because if you had, you would be here. Right? Oh my god. My eye. Anyways, my neck is not very good, but I'm still willing to speak for you guys. So I'm not lazy like you. Alright. So, we have to find the electric potential at point A, midway between two charges. Okay. Physicsaholic point from me. If there's a option 0 for 0, if there's option for 0, always make sure, check if the answer is actually 0 or not, okay? Forget doing all the calculations, just check if it can be 0 or not. First check that, okay? And there's high probability that the answer is 0, but let's check. We have to find the electric potential at point A here, midway between the two charges, this and this. Okay. We have to find electric potential. Okay, we have to find V. We have to find V. So, let's find the potential energy here. This will exert a force on this. Wait. Right here now? Right. Okay, this will exert in this direction. These two will be cancelled out. These two will be cancelled out. The main force will come due to this one and this one. Actually, it will come in the opposite direction because since they are like negative, and we're assuming that this charge in A is positive. So this will be like an attractive force. I'm going to change the color. This will be like an attractive force. And come on. Right. So this will be an attractive force. And this will be an attractive... Okay, come on. Ah, man. I did not even need to do that. Okay, this and this, right? Cool. So the forces will be in this direction. And the resultant will come in this direction. And the distance this here, this 2L, this is L. So it will be 2L squared plus L squared. That is 4L squared plus L squared. That is 5L squared. That is root 5L. That is root 5L. This side is root 5L. And this side is also root 5L. And did they mention any theta between them? I don't think they did. But the resultant would be in this direction. Wait, what are we even doing? Like, the potential energy, this Q1, A, Q, A, plus, oh, so yeah, these are in the opposite direction, so they will cancel out. But, I don't think they will cancel out. Would they? I don't think they will. So we have to find the resultant here. So this is a 90 degree. This is a midpoint. And ouch. Oh, so that means this is a 45. This is a rectangle. This side is L. This side is L. And this is 90. This is 90. This is 2L. This is 2L. Then the diagonal must divide them into equal angles, right? This angle equals this angle. Nah, I don't think. Yeah, they're not the same. They're not the same. But we know that this we know that this is a theta and this is a theta, and we know that this is also the same theta, right? So we know that we could let me brainstorm right here. This is the height is known. This is also known, so we can write it. What is hypotenuse by perpendicular? So we have what is perpendicular by hypotenuse? Alright, we have sine theta. So sine theta equals, what is that again? L by root 5L. That's 1 by root 5. Okay. Okay. So this will be sine theta, and this will be 2 sine theta. Okay. So I think these two will add up. U1 plus U2 will be 2 U sine theta, right? Of course, and that will be KQ KQA. That's minus, no, direction we will do later. Minus KQA by distance between them is, the distance between them is root 5L plus KQA 5L, but it's gonna be sine theta, right? Will be a sine theta here and a sine theta here. So that will be 2KQA by root 5L sine theta, and that will be 2KQA KQ. Oh yeah, we don't need A because we're finding the potential here. Okay, so that will be 2KQ by root 5L times sine theta. We know it's 1 by root 5. Oh, so it will be 2KQ 5L. Is this in the options? No. But we were close. We were close. But where did we go wrong? Where did we go wrong? Everything was like fine. We did this, and the resultant will be here. So this will be F. This will be E, R, if you like remove the one R. So this will be it. No, that would be U. Then this will be the resultant. KQ, where did we mess up? That's L. Sine theta would be L by root 5L. That would be 1 by root 5. So we have 1 by root 5 here. We have, I don't know, where did I mess up? It's time to go to ChatGPT for help. Gosh. Really stressed out by this one problem. Wait. I'll have to ask Chat Noir GPT for this problem. Okay, Chat. No way. So, ChatGPT is saying that potential is a scalar quantity, and yes, I indeed applied vector sum. So like, yeah, potential does not have any direction, right? So I don't understand, bruh. I just don't. Can you solve? I'll ask him to solve it. Can you solve it? Okay, he's trying. So it's KQ by R. So they are not canceling out. Minus Q. It's saying it's 0, it's not. stupid chat is saying it's 0. Come on. Yeah, it is reaching. So yeah, I gotta add all of them. Why there's 1 minus and 1 plus? It's not the direction then. I don't understand. I consider them with their chart. I mean their VA plus VB plus VC plus VD, right? Yeah. Oh yeah. Potential would be just Q, and that's not minus Q. Why did it? That's not a minus Q. That's not a minus Q. That's a not. I think that's gonna stay right there, and the other one is gonna get cancelled out. What do you say? I still do not understand, bro. Bro, what? Let's revise the slides. I think we're missing a point here. Oh gosh. So in the next problem, saying V naught is K, Q naught R, V equals to 0. Wait, how are they cancelling out? If it's a scalar thing. So this is Q and this will exert a force 2Q here. This will exert a force 2Q there. This will exert a force. Man, come on. How are we subtracting? How are we subtracting? Oh. I still do not understand. Okay, potential by a ring is KQ by R, constant. Potential by a semicircular ring is also constant, KQ by R. Okay. But it's the same as that for the circle. Oh, doesn't really matter, right? And for a house here, that's also KQ by R. And for a ring, that is for a full-blown ring on its axis. It's the same formula, KQX. Okay, this that. But here instead, we don't have to ouch, my stomach hurts. Just remove the Q part and just root them. Yeah, remove the Q part and also kind of. Okay, there's this formula that we should remember at all costs. Yeah, that's the only different one. But we don't know the potential energy. Man. Bibig mo sarap kasi. Oh god, we get the potential. Gosh, dipole. Oh, come on, I really don't want to deal with this dipole shit right now. Oh man. have like a lot of chapters to do still. I did not understand the concept of potential. They're all positive, so no one will cancel anyone out. They will add up. Right? Right? Yes, they will add up. They won't cancel out. Oh, so I was canceling it out. I think we just do not have to. We have to just not cancel any potential out. Right? So these two will be like added. So that will be 2kq squared by, what's the distance here? What's the distance here? L. Great. Plus, due to this and due to this, root L, root 5L, 5L, will be 2kq squared by L by root 5. Of course. That would be that again too. So if we will add them, it will be 2k. It will be more than that. Yes. Oof. Okay. Oh yeah, we have to consider the signs too. So we gotta subtract that. So we have 2kq squared L minus 2kq root 5. So we can take the 2kq out. 5L out. Oh, this is so easy. Come on, that was easy. And I was stuck at it for like so long for no reason. Come on, that was so easy. What I was doing is that I was definitely doing a vector sign, which I shouldn't have done. Come on. That was really, really stupid. So pissed at myself. Wasted so much time and potential. Okay, potential at the center of the ring. Yeah, we know. Yes, this one's important. I would want to write it down. Oh God, we just have to do the dipoles after this, and then we will be free from electrostatics, man. Too much at once. Okay, so we have equals kq by a squared plus x squared. That's due to a circular ring. Just two formulas equals kq by r. Kq by r, right? Just two formulas you have to remember. Sorry, excuse my French or weird. I don't know what accent was that, but just ignore it. The relation between electric field and potential. Oh, in 1D. Okay. So what in 1D? What do you mean in 1D? What do you mean in one dimension? Oh, so we can like either move forward or backwards. That's what it means. This is 1D. So it's the derivative. It's differentiating v with respect to x, and we will get electric field. Okay. How to get force? from potential, we integrate it, and how to get potential from force we differentiate it with respect to x. Easy, no big deal. Okay, in a certain region, I should probably write that down. Right. Okay, so that would be in the region space with volume this electric potential is found to be 5 V throughout the magnetic electric field in this region. That what? The magnetic electric field in this region, in certain region of space with volume this, the electric potential is found to be 5 volts throughout. Okay. If it's like, oh, it's the change, yeah. And if it's constant, electric field is 0, because it's definitely, oh, yeah. E equals minus dV dx. And if V is constant, then E is 0. Oh, the slope curves, shit. Man, what the hell is even that? What kind of graph is that? It's a really weird curve, so why it's like up here? I need explanation. I kind of totally forgot. How to find change in potential when EF is given. Whatever. Slope is dx dy by dx. dV by dx, that's the slope. If it's positive, then electric field is positive. If it's negative, then electric field is negative. Oh, we know in 2D and 3D, but in 1D it's E dx. Ouch. Ouch. So no vector in 1D, but vectors in. Cool. Okay. Yeah, whatever. Yeah, and this gives potential drop. Isn't it like the change in potential? Yes, that's change in potential. Okay, whatever, baka. And I'm so done. I don't want to do it anymore. Oh, what? So this area will give us, yes. How is it E dy by 2? So sine parallel is equals to that, and sine perpendicular equals that. So height half base into height, that's basically that. Okay. Cool. We're fine, we're here. And after that, we had to do current and electricity and so many other chapters. Holy shit. Oh, I did it. I'm not ready. And these are too much. A lot of them. This is just so not fair. This is just so not fair. It's been 2.5 hours. Man, we're suffering so much. because what a vulnerable state I am in. Well, I'm not vulnerable. I am strong. Okay, and I got this. I really don't feel like studying anymore. I need water. Oof. Okay, let me get myself some water. I'll be right back. तो नींद आ रही है 4:30 हो गए. God, I feel sleepy. Damn. I feel like really, really sleepy. Ooh. I've been getting, I got so many warnings. The audio stream's current bitrate 0 is lower than recommended bitrate. We recommend that you use an audio system bitrate of 120 kbps. It's lower than recommended bitrate. We recommend that you use a stream bitrate of kbps per second. What is that supposed to mean? The stream's current bitrate. It's bitrate. Oh my god, so embarrassing. I'm not dyslexic. It's just I did not just read bitrate bitrate. No, sorry, I'm sorry. So it's bitrate and it's lower than recommended. Do I give a shit? No, I don't. So, it's, more than 2.5 hours. God. Man. So, like, should I, like, take a break or something like that? Okay, all they're doing is taking a break. Oh, man. I want to sleep. Okay, fine. Let's just go through it like really quickly, okay? My mic is on, right? You all can hear me, right? Let me check. So, no, I am audible. So many of the slides. God, we know equal potential surface, right? Yeah, we know. The angle between the electric lines of force and the equipotential surface is 90 degrees. Everybody knows. E equals potential drop by D. In a constant field, though? In a constant electric field, okay. Finally, dipole. Dipole is a combination of two charges of same magnitude and opposite nature placed at a separation. Okay, fine. God damn. Finally, these dipole bitches. I tell you. Dipole is a combination of ion. Fuck that. No, let's write P equals Q times D. Right. Let's P mod P vector mod P vector. I don't know what. Okay, whatever. So there's a charge, positive, negative, equal magnitude, and we take the directions from from negative to positive. For some reason, we know why we do that, because this is converging. What? No, but that is not how it works. And I don't know why we take it like that. From my logic, it should be opposite, but whatever. Okay, the dipole moment. Yeah, whatever. Basically, charge into distance, nothing much. Both charges will be the same. Oh, polar molecules are molecules having permanent electric dipole moment. Yeah, that's true. Okay. A very nice question. The similar point charges placed. Two equal and dissimilar point charges placed at a short distance. Yeah. So this dipole thing works for short distances only. Okay, yeah. Yeah, we know all this stuff. Okay, now we gotta find electric field on axis, on equatorial plane, and at the general point. Gosh. This is just so annoying. Come on. Okay, it's basically the same stuff with just dipoles. Some things will be different. Okay, man, I'm like done with this chapter, like literally done. Oh god, चलो निकलो. Damn. Alright, so I really do not feel like studying. I don't know why. I it's not like it's hard or something. It's just I'm like bored. It's not. I was here to make it interesting, but who would make it interesting for me? Huh? What happened? Why is it like that? No. Oh no, did I crash it? No, I crashed it. Shit. No. No way. What is going on, man? What the hell did I do? Oh, God. You know what? Only one option. I can't believe Edge would do something like that. So there's no option for, like, yes. I cannot believe you guys. That looks so weird. Whoa, I look so weird when I do that. Anyway, so we're back. Let me set my hair. What's wrong with my hair? I think they're fine now. Okay, just a little more to bear. Gosh. I'm alright. I want to move on to the next chapter. I want to take a break, but I have a test this morning. Wow, R's are cubed. I don't know what that is. And on axis, it's what? It's the same? The same? No, it can't be the same. No. Yes, that's not. On axis, it's 2kp by r cubed. And on equatorial plane, this is at the equatorial plane, and the z axis, A is 2 times the mod of this. Yeah, whatever. EA equals 2E equatorial. At ZMR, of course. Point charge is proportional to that dipole. Yeah, so we basically increased one R. Didn't we do that? Gosh, man. Electric field and perpendicular bisector of a dipole. That's minus R, right? Yeah. Okay, at the general point, E in general will be KPRQ. Are you ready for this? 1 plus 3 cos squared theta. Oh my god. Formula is insane, bro. Not gonna lie. Insane. What is that again? ER and ET. What's ER and ET? What's ER and ET and the resultant of this? Or we can just do that too, right? So the resultant of this will be under root the sum of the squares of them. Okay. ER equals 2kp cos theta by r cubed. ET equals kp sine theta r cubed. Oh my god, it's easy. Bro, it's easy. And E equals root E squared T plus ER squared. Not that much of a big deal. And tan alpha equals tan theta by 2. That does not mean that alpha equals theta by 2. That is not what it means. 2 point charges, blah 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 blah. The magnitude of electric field intensity at distance r. Well, electric field we're talking about, right? Oh, this is the formula. Oh, it will be proportional to r cubed. Yeah, that was obvious. Intensity of electric field depends on the distance of r due to a dipole as related as r cubed. Inversely proportional to r cubed. Potential on axis of dipole, same thing, but just one less r. This is on axis? Really? And then at potential it's 0, okay? We at axis VA equal KP by R squared and VE equals 0. Oh, that's kind of cool. That's kind of cool. Alright, and V General equals kp cos theta by r squared. That's easy. Man, that's easy. Ouch, my stomach. Ouch. I don't know why, but it hurts. Why so much pain in my ouch? Oh, I don't know why my stomach hurts. Maybe it's because, oh my god. Maybe it's because I had milk coffee or spicy noodles, which were way too spicy. Honestly, they were really spicy. Not good for anyone's stomach. Ongoing from point charge or small electric dipole. Man, shut up. My stomach hurts. I'm not lying. I'm really not lying. It really does hurt. Should I stop for a while? I think I should take a break. I think I should take a break. Maybe a little 10-minute nap. It's just, I could have completed it really well, but my stomach hurts really bad. It hurts really bad. Alright, I think I'm gonna go for a while. Should end the stream though now. We are so close to our target, it's fine. Only 1 hour left. So we are how many hours in? Almost 3 hours. That's a huge deal. Chris. Alright. I think I'm gonna sleep for a while. If you guys don't mind. Alright. I'm gonna sleep for a while, okay? Till then, I'll be right back. Okay? Just after 10 minutes. So it's like almost 6, just half an hour. My stomach feels great. Not great, like better. Wait, okay? I'll be right back. guys, finally the chapter finish. Sorry, I know it's so weird, but I'm just like listening to some really good songs. I just can't like control. Can you guys? Alright, let's get back to work. We completed the chapter on my push and stress, so now we're moving on to capacitor. Let's get started. By the way, guys, 4 minutes and we're miserable. Should I end the live stream at 6? 3 minutes later. I guess I should. Alright. I did this first. Revised this up like 8 minutes. That's like a lot of time wasted. Really, man? I should have like worked faster. This chapter was not even worth it. Like, come on. So, anyways, it was really nice having you guys. I think I'm concluding the class way too early. We still have like 3 full-fledged minutes. We could study in those 3 full-fledged minutes. Like, can't be out. It hurts. Oh, it hurts. It really does, you know? But anyways, can you guys like guess which song I was listening to? Like, from my lip, can you like read my lips? If you can, just comment down below which song I was listening to. Alright. Okay, I'm so cringe. Okay, capacitance of a single conductor. How it works? We don't know. Okay, V is proportional to Q and Q is proportional to V, and capacity is basically charge per unit voltage. How much charge per unit voltage? यानी कि basically एक थैले में मेरे कितने आम हो जाएंगे, right? So वैसे ही एक voltage में मेरे कितने charge आ जाएंगे. Exactly like that. So yeah, I like how I like interpreted it. I don't know how to speak. I like how I made an analogy for that. It's a really nice analogy. Don't you two think so? So we're 1 minute, officially like 1 minute away from reaching our goal. And wait, let me should we start the countdown? I think we should. Alright. Alright. I'm presenting my screen. And yes. The time, it doesn't show time. I'm sorry. Man. Now you know it. Alright. switch back to this, and yes, yay, it's officially 6 a.m. in the morning, you guys. It's officially 6 a.m. in the morning. We have completed our goal. We've reached our goal, and I stayed up all night. Okay, I slept for like 10 minutes. I swear it was 10 minutes. I didn't sleep for 20 minutes. I slept only for 10 minutes. The rest 20 minutes. Okay. I did study fine. But for 4 hours straight, great job, y'all. It's really been 4 hours, y'all. Oh my god, it's really been 4 hours. Okay, so this was really nice having a stream with you guys. I'm gonna end the stream, okay? Bye. I love you guys so much, and cheers to us. Nobody came though, but in case if you're watching this in the future, yes, I did the stream alone, all by myself. Nobody came. But if you want to like study with me, I'm always here. Not always, but yes, my channel is here, and I might upload. If you want to study all night, I'm always here. Again, not always. Barely here. Anyway, it's time to bid a bye, guys. Ciao. Ending the stream in 3, 2, 1.